Let's start. Okay, for the entire chapter, it basically split up into those 3 points. Alkane, alkenes, alcohol, carboxylic acids, and macromolecules. So let's look at a few things. Okay, this term hydrocarbon is something that you will see quite frequently. Hydrocarbon simply means a compound that contains only carbon and hydrogen. So these two substances, they are hydrocarbon. These two is not hydrocarbon because they contain other elements. Macromolecules, some are hydrocarbons. Again, don't need to memorize which one is, which one is not. You need to understand hydrocarbon is just C and H. And then compounds, they are split into what kind of special structure that they have. The special structure that they have is called functional group. So functional groups are basically substances have that the special structure that the substances have. So under the concept of functional groups, okay, let's introduce this. So all these are the names of the different families. So for example, let's take a look at something that we are very familiar with, acids. Okay, all acids have this COO group. This COO group is called a functional group of acids. Okay, one of the more common items that we have seen before, ethanoic acid, CH3COOH. So when we draw into this kind of structure where each carbon has 4 bonds, oxygen 2 bonds and hydrogen 1 bond. Oh, please give me a second. This COOH group here, this is the one that we're talking about. This is the functional group of acids. So even for compounds that you have not seen before, as long as they contain this COOH group, it means that this particular substance is an acid. Straightforward. Okay, this whole cluster of atoms, they are called the functional group of acids. So I scroll up for you in a while. Hang on a bit. So for alcohols, this is the OH. This OH group is also known as the functional group of alcohols. Again, another common one is ethanol. And this is how it will look like. Okay, when you look at a compound, do not be confused over this has OH, the acid has OH, then how come the alcohol is not an acid? Because there's no C double bond OOH. In order for your substance to be an acid, it must have C double bond O with the OH group, the one in red. Same thing for the alcohol, it simply just have a OH at the end. So that is your alcohol group. Okay, next, let's look at alkenes. So as you can see that the trend goes, it means this substance here have a CC double bond. Again, this is the functional group of alkene, the one with the E. Notice there's one with the A, there's the one with the E. The one with the E is is the one with the CC double bond. So I can draw for you a sample, which is ethene. Ethene, ethene molecule has a CC double bond. So from here, we have structure C2H4. And this is your functional group of your alkenes. And on the last on this page here, alkanes, these are the ones with no distinct functional group. It doesn't have anything special. Okay, that's all. All right, please help me jot this down. And we'll scroll over in a minute. Any question to sound up? Okay. The last two substances are substances, oh, this one, is it? Okay. So the last two groups are the esters and the amides. I won't show you a specific example because they are big molecules. So generally, this CO here has is a bit similar to your acid. Okay, you notice it's very similar to the acid. But normally when it's an ester, okay, these two can be anything. But this one, right, must be a carbon. But not really that important to know. Just know that if this must be carbon, because if it is H, right, it is an acid. Because if it's an H, it will have been a C double bond O, OH. Then that is an acid already. That's not an ester already. So don't mix up esters and acids. Just being that the one bonded to the O must be a carbon. For organic chem, very simple. It's either with carbon, with hydrogen, and so on. So if this is a H, it turns into a COH, like what you have here in the acid. So it doesn't make sense anymore. Okay? And how you form all this, how come there's a C over there and not a H over there? Uh, 2 more weeks you will see. And the last one, an amide linkage. This is an amide group, CONH. This is how it looks like. Okay, I'm going to use this amide to show you something about drawing this kind of formula. This kind of formula is what we call structural formula. And you notice that every every stick it represents a bond. So you see over here that carbon has 4 sticks. Oxygen has 2, nitrogen has 3, and hydrogen have 1. All these are linked to their electronic configuration 2, 4, 2, 6, 2, 5, and 1, such that they need to gain 3 to be stable, gain 3 electron. Sorry, this one is gain 4. Oxygen needs to gain 2. Nitrogen needs to gain 3. And hydrogen needs to gain 1. For this reason, this is the number of bonds that you will need to draw when you draw this structural formula, all based on their electron configuration. Okay, please help me jot everything down. Digest. We'll move over to alkanes in a minute. So you see the first sentence it says they have a general formula. Or then later I scrub for you, okay? I proceed with some first. I left a bit only. Okay. Remind me after class. Okay, so alkanes here, again, we say that they are hydrocarbons, which means they contain only carbon and hydrogen, and that they have a general formula CnH2n plus 2, where N represents the number of carbon in the structure. So depending on how many carbon you have, you just suck in. So as we mentioned, hydrocarbons contain only hydrogen and carbon atoms, no more. Okay, and then for the alkenes, later we'll use the formula. But for now, we look at this part is the naming. Okay, the names, they normally ends with a and E. And then the exact naming of it, right, is determined by the number of carbon atoms present and the functional group that it present. In this case, the functional group, they don't have any functional group, right? So this is just a and E. Okay, homologous series. Okay, so what is a homologous series? Homologous series is a simple, it's a complex term that simply means it's like I can call it a family of alkanes, or we can call it the homologous series of alkanes. It applies to other organic compounds also. We can call it the homologous series of alkenes, of alcohols, of acid. It doesn't matter. The idea is just this is just a name for a group of organic compounds. So when you see the terms homologous series, it's just a collective noun for organic compounds. And one of the more important things that you will want to know is that if they lie in the same series, okay, in a homologous series, each hydrocarbon differ from one to the next hydrocarbon by a CH2 group. So that means consecutive members of the same homologous series. Differ by a CH2 group or differ by a mass of 14. Why 14? Because CH2 is 14. CH2 is 12 plus 2. So when you see members, their MR differ by 14 from one to another, that means they likely to be in the same family. Let me use this as an example because this CH2 thing do appear quite frequently. So for example, okay, this is an example here. I have option A, a compound that is C2H4, C2H6, C3H4, C3H5, C3H6, and let's say C4H6, C4H8. If the question asks you which ones are in the same family, they belong to the same homologous series. So as we see that one differ to another, to the next member by a CH2 group. So for the C2H4, his next member should be additional of a CH2 group, which means C3H6 belong to the same family as C2H4. And if you move on to the next one, another CH2 group, that means C4H8 also belong to the same family. So these three guys, they belong to the same family because as you move from one hydrocarbon or one organic compound to the next one, they differ by a CH2 group. So even if you do not know what this substance is, it doesn't matter. You're supposed to be able to know that when you move from one to the next, they differ by a CH2 group. So others that is also belonging to the same group, you might have seen C2H6, the next family should be C3H8. You notice there's no C3H8, so not possible. And then C3H4, his next family is C4H6. So technically, these two guys are also in the same family. Okay, this is how we gauge members belonging to the same homologous series. All right, any question? That's the whole point of that bullet over there. Okay, no question. This one is mass. The mass or the MR is more than by differ by 14. Okay, and the last bullet on this page, we have the structure as we mentioned just now. This is the one that it shows you carbon must have 4 bonds and things like that. So nothing much here. So this is exactly what we did just now. And of course, we have one more nitrogen. There must be 3 bonds. Let's look at this. So when you look at the formula, just now we mentioned the general formula, CnH2n plus 2. So if you sub the number of carbon present, you will get the respective formulas over here. Okay, so these are the underlined portion, these are the prefixes. These prefixes tells you the number of carbon atom that is present. When you have meth, you have 1. That's why methane is CH4. There's only 1 carbon. Then there's 2, 3, 4, 5. This is 6. We have 7. And then the last 3, we have 8, 9, and 10. Now, do you need to memorize? Not exactly. But you can see that I would say the first 4, you probably need to memorize a bit because there's nothing that is of that we have seen before that has this kind of naming. But number 5 onwards, you'll notice they are all geometrical shape. Pentagon, hexagon, heptagon, octagon, nonagon, and decagon. So other than the last number 5 onwards, the first 4 you probably need to kind of remember. Okay, so other than that, nothing much here. And you can also see here from the molecular formula, they differ by a CH2 group. As you move from one member to the next, you add a CH2 to the formula, and so on as you move below. Okay, structural formula, every carbon needs to form 4 bonds. Every hydrogen needs to form 1. So you will see the structure will look something like this. So it's quite duplicate, so I won't make you all draw everything. But if you all want to, you all can on your own time draw it. Let's look at butane. So 4 carbon, how do we draw 4 carbon? Normally, they are in a straight line. So we have 4 hydrogen at the bottom, 4 hydrogen at the top, 1 on the left, 1 on the right. So you have your butane. So if I do my hexane, it's the same thing. 6 carbon in a row, 6 hydrogen on the top, 6 hydrogen at the bottom. So we have 12, 1 on the left, 1 on the right. So we'll have 40. Okay, so the structure is quite similar. After class, you all can fill in yourself. But I need you all to look at the concept of boiling point. Over here, I explained that the boiling point increases down the group. Why is it so? It's due to the increase in the intermolecular forces between the particles. Because the larger the molecule, the greater the intermolecular forces of attraction. So more energy is needed for the larger particles, and hence the melting point or boiling point is higher. So this means that the more carbon you have, the larger the molecule. The larger the molecule, the stronger the intermolecular forces, the higher the melting boiling point required. Okay, any questions regards to number 1, the naming? Based on the number of carbon atoms, we have the meth, eth, prop, bu, pent, hex, hep, and so on. Number 2, how to draw the structural formula for the basic alkane molecule. Number 3, how to use the general formula of CnH2n plus 2 to derive the formula for the alkanes. Number 4, do notice that consecutive members, indeed, their formula differ by a CH2 group. Okay, and number 5, the structure size will affect the melting boiling point. The larger, the higher the melting boiling point. So that's the basic things that you will see on this page. Okay, any question? If not, I'll just leave this here for a minute for you to jot down whatever you need. Right. Today is the first day for organic, so I'm not going to do isomerism today. It will be a bit overwhelming. So we'll skip isomerism for today, and we look at some of the easy things like properties and reactions. Get you all started a bit on this. All right, let's take a look at physical properties. That's within your, I'll say it's the trend. There's wall of text here, so I can roughly give you this. Size of the alkane increase, or the number of carbon present increases. Okay, both are the same thing. There are three trends. Number one, as we mentioned just now, the larger the molecule, the melting boiling point increases. Number two, something we call viscosity increases. This means that it's harder to flow. Number three, flammability. Decreases. That means it is harder to burn. Okay, so this is in a nutshell. The general trends of your organic compound as the molecule gets larger, more carbon atoms, MPVP rise, they become harder to flow, and they become harder to burn also. Give 30 seconds, please jot this down. All right. You look at the first few bullets, it is basically the same thing as you have seen in the previous page. Um, number of atoms increases, size increase of the molecules, then intermolecular forces increase stronger, then melting boiling point increases. Okay, so this here is just the explanation. I think this one, right, this word, I will prefer to change it to the size of the molecule instead. Otherwise, teacher might say that it's too big. So it's the molecule size increase. Okay, so this is for MP/VT explanation. For the other two, we don't really need. Let's see, what do you mean by every point? Every point for in which context? Or you mean this one versus all the points here? Is it? Oh, this one is good enough. But of course, for the melting boiling point portion, that's the explanation. This explanation portion can appear in bonding, all this also. So the explanation part is more no choice. But for below, right? I kind of say so much, but actually it's really not that important. Okay, we don't have to explain why when there's small carbon, the viscosity went up, or when there's small carbon, flammability goes worse. Okay, the explanation is not that important. So over here we have the number of carbon atoms. When they increase, it gets harder to burn. The flame becomes sootier. Okay, what is soot? Soot essentially is just carbon solid. This is actually the explanation. Those that I just tell you only, but it's not important to know. But again, for the sake of section B, first question where they can teach you something on the spot, right? One of the easier way to explain why bigger molecules are very hard to burn is the carbon-hydrogen ratio. Because hydrogen burn very, very well. And because hydrogen burn very, very well, if your structure, right, it has a very high percentage of hydrogen atom, then it technically burns super well. So if you look at methane, right, CH4, the CH ratio is 1:4. If you look at the next member, C2H6, it drops to 1:3. And if you go further, like C10H22, it drops to 1:2.2 already. So you can see as the molecule gets bigger, the hydrogen gets progressively lesser compared to the carbon. So because of the lesser ratio of hydrogen, right, in the formula, it makes the hydrocarbon not burn that well because the hydrogen part is the one that makes them burn pretty good. That's why methane is a super burning fuel. And when they burn it, they don't produce any soot. Very, very hard for methane to produce any soot because it simply burns off so well. Okay, so that's the rough idea, but need to know or not? No, I don't think you need to know that. So you just need to know this. More carbon, flammability decrease. So they don't burn so well. Okay, the last trend that we have is viscosity, the ability to the ability to flow. So harder to flow with bigger molecule, more viscous. So example given here, things that's very viscous is like your ketchup, lava, peanut butter, they don't flow well. Less viscous is like water, tea, coffee, and so on. Okay, for the less viscous one, that's the general idea what is viscosity. So as you can see, when the number of carbon atom increases, when you get more and more carbon, the liquid texture changes from flowing well like water to eventually like ketchup. So we have, in terms of the number of carbon atoms, the more carbon atoms you have, the viscosity will rise. So this makes it harder to flow. So that's our three physical properties based on their difference in the size. All right, let's look at chemical reactions. There are three major ones. Combustion, substitution, and cracking. Cracking is the exact cracking that you see in paper processing. But for today, I'm not doing cracking because we need a bit more knowledge on the next group alkenes before I can do it. So for today, we'll look at combustion and substitution. Okay, so let's look at what is combustion. Generally, all hydrocarbons will undergo this. So the process is when the molecule that you have reacts with oxygen to produce CO2 and water. And more accurately, we say that this is actually steam. It's produce CO2, water. So this is a typical reaction. Now, when this thing occurs, this is called complete combustion. Now, complete combustion occurs when you have so-called sufficient oxygen gas. When we have another kind of combustion, which we call incomplete combustion. This is done where there is insufficient oxygen and you will produce two more products. Okay, number one is your soot, which is your carbon. Number two, in terms of the gas, this is your carbon monoxide. Okay, a very clear example of our when you actually observe this complete and incomplete combustion. Okay, in the laboratory, when you close the air hole of your Bunsen burner, you will see that it is orange flame. Okay, this orange flame is caused by your soot. The soot causes the orange flame. Why do you have soot? Because when you close the air hole, there is limited amounts of oxygen, and hence you actually get incomplete combustion. That's why you will see the flame being an orange flame. And when it's an orange flame, there is soot present. And when you do have an open air hole, you notice that the flame is an invisible flame. Sometimes we see it as blue, sometimes we see that it's actually invisible sometimes. Okay, because over here you can't really see it because there's no soot present. And when you open the air hole, you actually have sufficient oxygen. So this is a simple illustration to show you that in real life, when you do have complete and incomplete combustion, this is the kind of products you get. Sometimes on the road, you might see some vehicles giving out black smoke. Black smoke is also soot. So this means that the fuel that's burning within the vehicle has undergone incomplete combustion, and then as a result, you get soot formed, and that's when they get a smoky produced from there. Okay, so this is the difference between complete and incomplete. Yeah, please help jot this down. A minute sign, no question for me. I'll move on to substitution. Okay, let's look at substitution reactions. Now, first of all, there's this term here that you need to see. Saturated. The opposite of this is unsaturated. So when we have saturated compounds, it means that we are not able to add any more atoms to it. And that all the bonds, okay, because it's saturated, it's likely to be single bonds. So why is this important? When you move into the next group, it will be more pronounced. But as of now, do know that they are considered to be saturated because they are all important single bonds. Okay, when you are saturated, you are said to have single bonds. Okay, for alkanes, they undergo what we call substitution reactions with halogens. And it is done in the presence of sunlight. Sometimes we call it UV light, ultraviolet. Okay, either way, it's fine. So you can see from the name and the chemical formula. Okay, we see that this methane, which is your CH4, reacting with your chlorine, which is Cl2, you form a compound called chloromethane, which is your CH3Cl, and the last part HCl, hydrogen chloride. This is not hydrochloric acid because hydrochloric acid needs to be aqueous. These are all fundamentally gases. So if I were to put the state symbols in, they are technically all gases. So what actually happens in the structure? Let's look at the structural formula or the structural equation. We have the methane. We have the chlorine. Okay, well, after they react, in a substitution reaction, there is a one-for-one exchange between the chlorine and the hydrogen. So this will accept the chlorine. And the H get bumped up. Okay, simple. This is called substitution. Okay, next. To understand the substitution process, right, this is very, very important. For every hydrogen that is to be substituted, you will need one Cl2 molecule. Okay, so if you want to substitute more hydrogen, you need to substitute it with more Cl2. It's a must. You cannot say there's 2 chlorine here, Cl2, I swap for 2 hydrogen. No, you can't. That's not how it works. So they can only swap one time and it's done. So every H, you need one Cl2. Okay, simple. Now, let us, now you can see the structure over here. Let us explain the answer here. Why is it called chloromethane? Okay, ANE means that there is no functional group present. Because if there's a functional group present, I will name it either an alcohol or something. But because there's nothing here, you look at the structure here. There's no double bond, there's no OH, there's no anything special, no special functional group. So it will be under the alkane family. Why is it mass? Because in the formula, there's only one carbon atom. Why is it chloro? Because there is a chlorine atom, a single chlorine atom present. Okay, please jot this down. Slowly digest. Right, if no questions for this, let's move on. So where more than one hydrogen is substituted, we have to change the name accordingly. So you can see from here, I use bromine, and depending on how many you have, if you have two, we call it di. You have three, we call it tri. You have four, we call it tetra. Just like your tetrachloromethane, that tetra, meaning four. Okay, let's look at the over here. How do we get it to tetrachloromethane? So as you can see, this is tetrachloro, means there are four chlorine attached to the methane molecule. So visually, you can see that means that all the four hydrogen all gone away. They are all replaced by chlorine. That's why we have four chlorine methane molecule. It looks something like that. Okay, so when you look at this, there are a few ways to do it. I can do it in a single step. So in a single step, we actually have this methane molecule. Okay, and because we say that for every one hydrogen that you want to swap out, you need one chlorine. So in this case, because I have four over there, so I will probably need four chlorine. So from here, the four chlorine can do the exchange. Maybe this guy can swap with him, this swaps with him, he swaps this way, and he swaps this way. So after the swapping process, you get the four chlorine taking the place of the four hydrogen, and at the end, I have four of the HCl. So this will be CH4 plus 4Cl2, producing CCl4 and 4HCl. And in the naming wise, we have the word equation. Okay, we have something like this. Okay, to know every single hydrogen has to be swapped off by every single chlorine. Okay, alternatively, we can do a single substitution 4 times. Uh, CHCl here is a gas, so it's hydrogen chloride. Put a note here then. The HCl is not hydrochloric acid because the state symbol is gas and not aqueous. HCl aqueous. This is hydrochloric acid. Is it okay? All right. Okay, if you do it 4 times, what does that mean? I'll just do the chemical equation here. So that means I'll go from CH4 with chlorine. Then I do just one single swap only. So it becomes CH3Cl plus HCl. Then the CH3Cl react with another chlorine to give you CH2Cl2 plus HCl. So we sub twice. Then we sub again. CH2Cl2 plus another chlorine. You get CHCl3 plus HCl. And finally do it one more time with Cl2 and you get CCl4 plus HCl. But the overall equation is still the same. So in this case, the overall equation will still be CH4 plus 4Cl2, giving us CCl4 plus 4HCl. This is the overall equation. So you can also see that the names actually change from, you start off with methane, you get chloromethane. And from the chloromethane, you get 2 over here, so you get dichloromethane. And from your dichloro, you get your trichloro. And same thing, the trichloro will turn into tetrachloro. Okay, this is how you can do substitution to get to your tetrachloromethane, either by the single step way or the 4 steps way. Whichever step that's required, you see the question. Okay, a second. So after this cracking, I'm not doing today because I need to do alkene first. So after this, I'll be doing alkenes. You have no questions for the substitution. Okay, I'll leave this here a minute or two. You'll digest chemical reactions of alkanes. Then we move on to alkenes. Okay, so for the next group that we are looking at is alkanes. Their name ends with the ENE, and they have a general formula of CnH2n. And more importantly, they are the first one with a functional group. This CC double bond, this is the functional group of alkenes. Okay, and because of this presence of this double bond, they are said to be unsaturated. Okay, just now we were seeing this, and I asked you all to put a label that this is saturated. Saturated means there are single bonds, mostly single bonds present. And because alkenes, they have a CC double bond. CC double bond is not exactly single bond. It's a double bond really, as the name suggests. That's why we call them unsaturated hydrocarbons. Okay, the naming is the same case. Alkene ends with an ENE and so on. Okay, methane no such molecule. Why? If you look at this case, is unable to have a CC double bond. To have a CC double bond, you need a minimum of 2 carbon. That's why there's no such thing as a one carbon alkene. Okay, so in terms of this structure here, how do we draw it? Okay, this is how I will normally draw a CC double bond structure, and it's very safe. So normally I'll do this. There's only 2 carbon, so that's all I will draw. So ask yourself the first carbon here, how many bonds it has already formed? Okay, in this case, the first carbon on the left already have 2 bonds due to the double bond here. So basically, I just need to give it 2 more bonds. Okay, then you see that your carbon has 4 sticks already, then it's happy. The carbon on the right has already got 2. So that means it needs just 2 more bonds. And let's fit in the rest with hydrogen. You'll see that C2H4 is correct. The bonds are correct. This is how we will draw the CC double bond. Now C3H6. Now we have 3 carbon. So first off, I will also draw the CC double bond first, but the next one, there's no CC double bond. Okay, why? Because alkenes, they only have 1 CC double bond. Okay, there's other homologous series with 2 CC double bond or 3 CC double bond. So they are not alkenes. So in this case, alkenes, there's only 1 CC double bond. So it will look like this. So I have 6 hydrogen to allocate. Let's see how the allocation can be done. The first carbon has already got 2 bonds over here. So I just need 2 more. Then he will have 4 bonds. The middle carbon, the second carbon, has 2 bonds on the left, 1 bond on the right. So technically, he only needs 1 more. Then he has 4 bonds already. And the carbon on the right-hand side, the rightmost, have only 1 bond. So he needs 3 more bonds. So this is the structure of your 3 carbon alkene group. And when you place all this with hydrogen, you get the formula of C3H6. Okay, if I were to do the same thing for 4 carbon, same thing, I'll have a CC double bond, bonded to number 3, bonded to number 4, and the same trick goes. First carbon, 2 more. The middle carbon here has need 1 more. The third carbon has already got 2 bonds, so he needs 2 more bonds, top and bottom. And the rightmost have only got 1, so I'll have 3. And the rest will fit it with hydrogen atoms. And you can see that it fits your C4H8. The number of bonds per atom is correct. The total number of carbon hydrogen atoms is correct. Okay, so the same goes for the rest of the structure. Especially for those of you who are doing it for the first time, right? For C5 onwards to C8, if you want, you can draw the structure for me to see and then take photo as homework sent to me. Okay, especially for those who have done it the first time. For those of you who already done it in school, you just want confirmation, you can do this portion and then send it to me. Why I didn't ask for this in Alkane, because Alkane is super straightforward. It's the one with the double bond sometimes will screw up. Okay, so help me, especially for those who are seeing this for the first time. Okay, boiling point is exactly the same as what we did just now. The larger molecules, stronger intermolecular forces, higher melting boiling point. Exactly the same. Okay, and then physical trends, exactly the same as alkene. So you don't have to do it again. Okay, so in the same case as what we did just now, just a quick one, increase in the number of carbon atoms. The 3 trends, number 1, melting boiling point increase. Number 2, it gets more viscous, viscosity increase. And number 3, the ability to burn, flammability will drop. Okay, it's exactly the same as what we did in alkenes. Okay, before I move on to chemical reactions of alkenes, anyone has questions regards to physical properties, regards to the drawing, regards to the naming, regards to the molecular formula, and all the little stuff here that I mentioned about unsaturated, CC double bond, and all this stuff. Okay, so before I start chemical, can I give you all 1-2 minutes, especially for those who have seen this for the first time, to run through whatever we have covered. Then I'll go into chemical properties. Those with question, please sound up. Okay, as mentioned, they are unsaturated because of the CC double bond. So what reactions they undergo? Combustion. This is the same as the alkanes. Okay, they are exactly the same, so I won't do it again. Or the complete, incomplete combustion. Okay, they undergo something called addition reaction. This addition reactions is alkene reaction, or something with a CC double bond reaction. So we have 4 reactions over here. Today we'll do reactions with steam, alcohol, and halogens. And then addition polymerization, not doing today. This is the last chapter. Okay, so what actually happens in addition reactions? Step number 1, CC double bond is broken. Step number 2, the additional atoms are added to it. Notice in the previous part, right, we say it was substitution. They exchange. But in this case, it's added. That's why this reaction is called addition reactions. And do remember, single molecule product. Okay? They must only form one single molecule. Let's look at the process in detail. Okay, combustion I won't do again. Okay, combustion is exactly the same as alkene, all the complete, incomplete, same stuff. So I won't do it again. Okay, let's look at the first addition. Is addition of hydrogen. So in general, what I can tell you is alkenes, when they react with hydrogen, in the presence of 200 degrees Celsius nickel catalyst, it turns into an alkene. So let's take the case of ethene. Plus hydrogen. So what actually happens? Ethene will be, as you know, it's a 2-carbon alkene group. So I have a CC double bond, 1 on 2 hydrogen on each side, reacting with another hydrogen. Okay, I'll change the color for this so you can see the addition portion. So what happens is, just now as you can see, the first thing that happens is that the CC double bond will be broken. This was your ethene molecule. So when we break the CC double bond, it turns into a single bond. So this is gone. and I got two more bonds coming up. Why are there two more bonds coming up? Because remember, carbon must have four bonds. So if you break the CC double bond, now this carbon needs to bond to something else. So what comes in is the addition of hydrogen. So the two hydrogen atoms will each go to each side over here. And you will get ethane. Simple. This is the addition. You break the double bond and then you get the two hydrogen added into it. Any question? See, it changes from ethene to ethane because these are, remember, reactions of alkenes. So the alkenes turn into alkane. So then just like asking about the purpose of doing this, of doing certain reactions. For this particular case, there is actually an application. Okay, what do we use this reaction for? This application is the making of margarine. What it does is it converts vegetable oil in the presence of temperature, a certain temperature, nickel catalyst, it turns it into margarine. Now, how does this occur? When this reacts with hydrogen. Because vegetable oil has many CC double bond. We call this whoops. Okay, we call this vegetable oil because it has so many CC double bond. It is called a polyunsaturated compound. Why is it called poly? In chemistry, when you see poly, it means many. Unsaturated means CC double bond. So this, hey, what's happening? Okay, so this vegetable oil has many CC double bond. So it will add many hydrogen atoms and it turns into margarine. In this same process, the double bonds of your vegetable oil will be broken and then the hydrogen added across it and then you get your margarine. Okay, this is the application. Why do we use this in the first place? Okay, any questions so far? So this is the first addition, reactions, which is additions of the hydrogen to your CC double bond. Okay, we call it hydrogenation or addition of hydrogen. Okay, let you digest a bit. Okay, if no question for this, let's look at the second thing that it adds. Alkenes can also add steam. And these are the conditions: temperature 360 atm and this. So in general, I will say that alkenes, when it reacts with steam under the condition 300 degrees, 60 atm, H3PO4 catalyst, it turns them into alcohol. This is generic. And we can also see that in this case, this is one of the application is to form alcohol from alkenes. So again, let's take the case of ethene plus steam. Okay, we're expected to get alcohol, so I'll just straight away name it ethanol. Because it's 2 carbon alkene, I'll get 2 carbon alcohol. So CC double bond, this is your usual ethene. Now with the steam, again, I'll put it as H2O. So what happens in the reaction? As per all addition reactions, the CC double bond will be broken first. And we get 2 more bonds. So what do we add into it? We add in a hydrogen and the OH. So anything with OH, remember right in front, we say that the functional group of alcohol is this. So you turn it into an alcohol. So formula-wise, C2H4 plus H2O, and you get CH3OH. Or simply C2H5OH. All right, any questions for this? Oh, let's see, you meant that that means in this case your teacher didn't put as OH, but instead you put the OH as, that means okay, if you were to draw it, that means his answer will be this. Is it? This is alcohol structure number 1, alcohol structure number 2. Clarice, your teacher, they draw structure 1 or structure 2. Did they draw a bond between the O and the H for your side? Kaylee, yourself? And then Delcy and Ella, both of your schools started on organic already. If both of your school have started and you have reached this, oh, okay. Okay. All right. But Kaylee, if the question didn't say full structural formula, right? Will your teacher still accept this structure number 1 if the question didn't say full structure? Should still accept, right? So in a nutshell, okay, there is something called full structural formula. Full structure means you got to show everything. If the question says full structure formula, it must be number one. Okay, you must draw it number one this way. Then, should I draw it like this? NC, actually, I will not draw this because dangerous. You don't know the mud scheme. So normally, in all cases, right, I will try to show all the bonds that's present. I will not condense OH as like this. I will normally take structure number one. I feel this is a lot safer. This is a bit danger because you didn't show the OH bond. So I think you should do number one. Over the years, you also always draw number one. So do number one, don't have to condense it. Yeah, I think that is play safe. Okay, so please help me digest this. Jot down anything you need. Okay, I'm almost done already. The last part I finished, then we are done. With the halogens. The only reason why this is important is because of identification. I finish identification, we will call it a day. And most of the time when we do halogen reaction is with bromine. And when it reacts with an alkene, it will decolorize and turns colorless. And because of this, right, this is a test for whether something has a double bond or not. Now, what does this mean? Let me do a quick one. So in this case, ethene will react with your bromine and you will get something here. Okay, before we go into the name is a bit confusing. Let's take a look at the ethene again. It reacts with your bromine. Okay, your bromine is group 7 halogen. And in this case, over here, it is reddish brown in color. And after the reaction, we can see that because of the CC double bond, okay, we are going to break the CC double bond as usual. So when it's broken, you got two more bonds, and it will take the two bromine atoms. That's all. It's just the breaking of the CC double bond. And because of this, this reddish brown bromine will decolorize. Okay, this is also one of the tests to see whether something have a double bond. Because when you have a double bond, it reacts with bromine, it will turn it colorless. Yeah, it will decolorize your bromine. So let us name this guy first. This is this structure here. So first of all, I'll give you the full name. This structure is called 1,2-dibromoethane. Okay, how do we get this naming here? What is the reason for this name? Let's take a look. First off, ANE. Why is it ANE? Because there is no functional group present. No more double bond, no more OH, no anything. So there's no functional group. If it's because there are two carbon atoms. Bromo, because there are bromine atoms present. Dibromo means there's two bromine present. What about the 1,2? The 1,2-dibromo is to tell you that the one bromine is on carbon number 1. and the other bromine is on carbon number 2. Okay, this is your carbon number 1. This is your carbon number 2. Okay, we have to say the 1, 2. Why do we have to say 1, 2? Because if we don't say that, then how do we know where are the bromine? This is 1, 2 dibromoethane because the 2 bromine is on carbon 1 and on carbon 2. Okay, let me show you what happens if you don't say the number. If you look at this, you notice the 2 bromine is on the same carbon number 1. So to name this guy is actually called 1,1-dibromoethane. For the same reason that, why is it ANE? Because there is no functional group. Why is it eth? 2 carbon. Why is it dibromo? There's 2 bromine present. And 1,1 is to tell you that the 2 bromine are on number 1, on carbon number 1. So that's the reason why the numbers in front are important for you to tell where the bromine are situated. For those of you who are seeing organic for the first time, might be very overwhelming. But please help me to read this through one more time before next week's class. And if you need any help for whatever that we have done so far, right, please look for me. Weekend also can. But today, just take it as a new thing that's going on. After this, I just do one last part identification and then we are done already. Remember, the CC double bond will react with your bromine to decolorize it. Anything with CC double bond can do this. Remember that. Okay. Last one. My last thing for tonight. So this thing here. This is our bromine. Okay. This is reddish brown bromine. You can add bromine to your organic compound. You can add your organic compound to bromine. It doesn't matter. Okay. So let's say I add in some organic compound. I add in substance A into this. Okay, there are 2 results possible. Number 1, This is what we call reddish brown bromine remains unchanged. You can have scenario 2. It turns colorless. So we'll say reddish brown bromine decolorized. So when this thing occurs, whether is it reddish brown or decolorized, what's the outcome? So the outcome will be this. When it decolorized, my conclusion will be number 1, it could be an alkene, the one with the CC double bond. Number 2, it has CC double bond. Okay, like what we did over here. With the CC double bond, it will react with the bromine, it will break the double bond, it will break your bromine, then it decolorizes. So when your bromine decolorizes after A added to it, it means that it's either an alkene, it has a CC double bond, or number 3, our conclusion will be it is unsaturated. Remember, unsaturated means that it has a CC double bond. Okay, in the same way, if it remains reddish brown, number 1, I cannot say that it's an alkane, I cannot. I can only conclude that it is not an alkene. Let me write that nicely. Okay, it is not an alkene. Number 2, it is likely to be saturated. And number 3, it has no CC double bond. If your bromine remains reddish brown, that means no reaction. Okay, in this case, it means there's no reaction. No reaction means those 3 conclusions. If you have a reaction, it decolorizes, then it means that alkene is present, CC double bond is present, or it is an unsaturated substance. This is visually what you will see. Okay, that's the last thing I'm doing for tonight. So